We are software engineers from Wix, working at the data infrastructure group. For those who are not familiar with Wix, Wix is a platform for building websites and services. And today we are very happy and excited to walk you through the evolution of our online feature store, an essential part of Wix's data infrastructure. Um, I'm Tal Sheldon. I'm a software engineer and a lecturer at Reichman University. And I will start by giving you some introduction to our feature store, then some use cases, and then we'll dive straight into the architecture. I'll tell you about the high-level design, and then I will tell you about the previous implementation of that design and why it was so very bad. Then Guy, my colleague, will come here, take over and tell you exactly how we rebuilt our system to make it a lot more resilient. So what is a feature store? A feature store is essentially a database for useful pre-processed data, which is available both online and offline. This term originated from the need to standardize feature engineering when working with machine learning models. But in fact, this concept goes far beyond the machine learning domain. In fact, we had this service at Wix just like that a long time before this term became so popular. We just didn't really have a name for such a service. We have now. Just a quick disclaimer before I start. I'm sure some of you are familiar with feature stores, which is great, but please do not expect a textbook definition. It's an internal system, and we built exactly what we needed. Cool? Cool. So let's talk data. At Wix, our data infrastructure group is responsible for the entire life cycle of data, capturing every meaningful user interaction that the user is doing within our platform. We cover basically all essential user interactions, direct and indirect actions. We call these BI events, and these BI events help us understand how our users engage within our platform. Examples for such events are when user visits some page, when he clicks on some button, when he installs some application, basically every essential interaction that he's doing within a platform. So Wix is a fairly large company with a fairly large amount of data, and we have more than 40 billion events entering our systems on a daily basis. All these user interactions, they all accumulate to a pretty large amount of data. And our feature store is a crucial part of this data infrastructure. We're serving more than 2,500 features, all active, and all of them are updating in real time. So 2,500 features, I think it says 15, it's a mistake. But 2,500 features, I think that's a pretty large number. Every feature comes with its own background. Every feature has its own latency requirements. Every feature emerged from the hopes and dreams of some product manager. And our feature store is a self-service, which means that everyone at Wix is able to create and manage their own features and manage their life cycle of these features. And today, every microservice at Wix is using our feature store one way or the other, even if they don't really know it. So let's take a look at our main two use cases. First of all, our feature store powers the personalization engine that is used all across Wix. When users enter the editor platform doing whatever they're doing, then we are recognizing who they are and along with all their past decisions. Having this data available in real time is giving us the opportunity to provide them with personalized recommendations. So they'll be able to build their business and the website in a much more efficient manner. Second is the classic, of course. The machine learning platform is built on top of our feature store. When it's the machine learning its pipelines rely on our features to be with the most up-to-date data and with very low response time, so they'll be able to perform real-time inferences. If those features will not be up-to-date or will be very slow, then these models will simply not perform as expected. Critical models like fraud detection, spam detection, detecting harmful content, and many more, these are all critical models that must happen in real time. In most of these use cases, real-time updates are crucial to the integrity of our features. Whenever new data arrives, there is a very small time window in which this new data is still relevant. And if we pass that window for whatever reason, if we missed it for whatever reason, then this new data and this new interaction that the user just did may be already obsolete for us and no longer needed. So in a product perspective, this all may sound a little complicated, but eventually all these features, they all boil down into simple rules and definitions. For example, when was the first time the users made a purchase? When was the last time the users made a purchase? How many times did the user enter his editor in the past week? What are the last 20 installed applications that the user have installed in the past month? These are all actual and real features, and they all seem pretty simple, and they are simple to calculate overall. But I think that what makes it so challenging is the scale and doing it in real time, of course. So we need to run these calculations for every website and every user, and sometimes even for every session of a user at Wix. This means performing these calculations for more than hundreds of millions of entities across more than 1,500 features, which is quite a lot, 2,500 features. All right, so let's take a look at the architecture starting from the high level. And after we'll finish the high level, we will come back to the previous implementation of it. So users interact with the platform, doing whatever they are doing, living their dream. They're constantly generating BI events. These BI events are collected, enriched, and routed to the corresponding Kafka topic. We have a few hundreds of these Kafka topics, but remember that every possible Kafka topic is an optional data source for our features. But we won't focus on this data collection phase. We'll focus on what happens after the data is enriched and persisted in Kafka. So we're reading from multiple Kafka topics. The first phase we're going to do is we're going to filter out all the events that are not relevant to any of the features. After that, we're moving all the relevant events to the transform microservice, which is essentially a Java application that takes all the relevant events and transforms them into actionable commands to send to our feature stores database, which is Aerospike. Now, Aerospike is a distributed key value store, and we chose it specifically for its ability to perform real-time reads and writes in a matter of milliseconds, almost instantaneously, which is exactly why we chose it. Now, before Aerospike, we used HBase and Redis in some kind of Lambda architecture setup. As you can imagine, this Lambda architecture setup was quite complicated, and we needed to maintain a very complicated pipeline. So consolidating these two paths into a single real-time path reduced huge amounts of complexity. But I prefer not to think about that previous architecture ever again, so we won't focus on these stuff. And that's pretty much it. That's the gist. We read from Kafka, filter out all the events that are not needed, transform the relevant events into actionable commands, and send these to Aerospike for real-time persistence. And of course, that's a very simplified view. There's also a Spark job to backfill on historical data and write them to Aerospike, a read layer for our clients to read from, which merges the historical and the real-time data and exposed mainly by gRPC, and a management API for our clients and for us to manage the entire life cycle of our features. And I'm sure that, as you can imagine, there's a lot more places and many more data sources, authentication, authorization, but we're not here for security. So let's go back to the simplified diagram now. And I want us to add some numbers for context. So we're consuming from 150 Kafka topics. Each topic yields about 10 million events per minute. We filter out about like 95% of the data, which results in about 500,000 events per minute, which also emphasizes the need for such a phase, all the heavy lifting being done in the filtering. We pass these relevant events into the transform microservice, and the transform microservice builds the write commands to send to Aerospike, which results in about 400,000 writes per minute. Mathematically, it adds up because we're doing slight pre-aggregation beforehand. So that's pretty much in a high-level point of view. Now I want to walk over the main challenges that we saw so far. First of all, low latency, right? Pretty obvious, both reads and writes. Second, more than 100 Kafka topics. We're consuming for about 150 Kafka topics. Every Kafka topic has a different data source. Every Kafka topic is a different data source. Each one has different throughput, different amount of partitions, different schema, different whatever. Third, we have daily changes happening to our features, and we must propagate these features into our pipelines almost immediately without affecting it that much. And lastly, every event can correspond to multiple Kafka topics, to multiple features, which adds some layer of complexity if you think about it. So we went over the high-level architecture, and now I want us to go over the previous implementation of it. That's what happened before. Cool. So the consumption from Kafka and filtering was done by using an internal outdated streaming engine that we built on top of Apache Storm, and we added some SQL streaming capability on top of it. To handle the filtering, we maintained some monstrous SQL queries. And these monstrous SQL queries, they perform the filtering. And whenever we needed to update some feature, then we just took the corresponding query, we killed it, and we spinned up a new one. Now, this process of killing a query and spinning up a new one is what it does, actually. It kills everything in memory, and we lose all the data that is inside. So that is constant daily data loss every time there's a feature, which is not very cool, but that is by design. So after the filtering, we are sending these events to the implementation of the transform microservice, which in here is the web server via HTTP. And then the web server basically takes all the relevant events using some Java application. It creates write commands and sends these to Aerospike, and that's about it. So before we continue, I want to focus for a minute on the Apache Storm and the web server. I want you to know that all of these are in memory, right? Everything is in memory. There's no persistency layer in between. So it might sound pretty terrifying for a lot of you, and it pretty much is. But I want you to look at the upside here. Everything is in memory. It's super fast. It's super cheap. There's no redundancy. There's no additional disks involved, no replication, no fancy whatever cross-region. Overall, it's just data in memory going on with good vibes overall. So it sounds pretty scary. Yeah, but if this was 2016, it might have been a good implementation. And even for today's standards, for basic trend analysis, it might suffice as well. So it's fast and it's cheap, but it's not too good, right? So let's summarize the problems with this setup. First of all, legacy tech. We're using a very old streaming engine, Apache Storm, from 2016. The version is from 2016, pretty old. And overall, with Storm's decline in popularity, it's pretty evident that we needed a new streaming engine. There are many fancy ones out there. Second, we're sending the events to the Storm cluster from Storm to the web server from within the cluster. So we're sending the HTTP request asynchronously. And in order for us not to block the upstream data, then we're firing it asynchronously and forgetting about it because we don't really have any persistency layer in between. So what happens is if we send an HTTP request and the web server is down, so we basically fire events into the void. Not cool either. Every time there's a schema update, a deployment, some node goes down for whatever reason, then we lose all the data that is in memory. Also, as I said, data loss, not cool at all, both in the web server and both in Apache Storm cluster. Fourth, we handle scale by simply being over-provisioned. Before important events like Black Friday and so, we just scale out manually. But even if we had an auto-scaling feature, we would never have used it, right? Because we have daily data loss every time there is a change in a feature. So we can't really have auto-scaling because the data in the node will just die. Not cool either. And favorites, and lastly, and my favorite, is there is no delivery guarantee. We use our Kafka consumer is using the consumption from Kafka with the auto commit feature, which should promise us at least once delivery guarantee. But unfortunately, our consumption phase and our filtering phase are decoupled. So what happens is that even if the filtering phase fails for whatever reason, the consumption just keeps on committing the offsets and moving data to the filtering phase. So we don't have delivery guarantee of at least once, not in the Apache Storm cluster and not in the web server. So all these limitations led us to constant manual intervention, which nobody likes. This just are totally exhausting mentally and are totally mood killers to run Spark jobs, to backfill historical data, restreaming events. Kind of sucks. So now I'll invite Guy to come take over and tell you exactly how we rebuild our system.
So, thanks, Yutal. And good morning, everyone. My name is Guy Lavinar, and I'm a backend engineer with more over 10 years of experience. And in the last 5 years, I've been working on real-time systems. And today, I want to share with you the journey that we went through at Wix, how we moved away from the legacy system and build a solution that fit for our needs. Let's go quickly over the steps that we took. First, we defined the requirement. Then we explore some technologies. And lastly, I will show you the new architectures that we build. And finally, and the last one, I will share some key insights that we learned along the way. So let's get started. First, requirements. We understand that we need to do some changes. We want to improve the reliability and resiliency of the system to ensure that no data will be lost. Next, we want to have the ability to do a real-time update in the feature catalog, and while to ensuring that the updates of the features will not affect on the other features that are already running in production. And last one, we want to use modern technology with well support, great community, and get updates, not like Apache Storm. Let's break down this requirement a bit more. First, fault-tolerant delivery guarantee. Of course, we want to ensure that no data will be lost. Second, scalability and high throughput. As Wix keeps growing, more users create more data. It means that we have a lot of more users create more sites, and it means that we have a lot of more data. And our average throughput is 10 million requests per minute, events that we are coming. And we need to also support special events like Black Friday, Cyber Monday with high traffic. All that with low latency. We need to process the data quickly as possible with minimal delay. I'm sure that you can think on many other requirements that's relevant to this system. So we did well. Take a moment to take a look. After we defined the requirement, and we told you we are filtering more than 95% of the data in real time, it's really important for us to choose the right technology to stream processing agent. So we took the leading technology in the market. Let's start with the open source. We took Kafka Stream, Spark Static Streaming, and Flink. But we also checked managed solution, like Confluent managed solution of Flink. And on each of one of these technologies, we did a POC to see how they will perform in our environment. And the result, we create, and of each of these technologies, pros and cons. So we create a comparison table to choose one. Here is the similarity table. And I just want to touch about the cost. It really depends on your company infrastructure, on your team skills, and in the other end, on managed solution, you just pay on what you use. Let's continue the next table that shows the difference between the technology. As you can see, we chose Flink, and specifically managed solution by Confluent. Why you choose Flink and why managed solution? Flink was the best fit for our needs, and managed solution give us better support and time to market. It was really important for us. I say Flink, but what is really Flink? I took this definition from the official Flink website, but it's too long. So I created a simple bullet in the TLDR section. As you can see, it's really fit for our requirements that we defined earlier. And I want to show you a small demo. Take imagine a use case that you are a site builder, site owner at Wix. And you want to show how many visitors are visiting your site in real time. So in the past, it was really hard to do this data pipeline. You need to consume the data, handle late events, use Windows aggregation, and some more. But in Flink, and specifically Flink as well, it's really easy and readable. First, we need to consume the data. So we need to create a Flink table that consumes the data in real time from the topic, and now we can query it. Second, this is all 9 lines of code, very readable SQL that contains all the data pipeline. We have insert into, select, site ID, count, from, group by, site ID, and date format by minutes. So we have a consumer inside, aggregation, filter, and also produce. We need to produce the result into another Flink table that produces all the data into Kafka. So I just show you very readable, full data pipeline, Kafka to Kafka, and with aggregation. And the best part is it's run in real time and batch, and it's production ready. So I want to connect all the dots that we saw. We saw the requirement. We saw the testing technology and why we chose Flink. And finally, we arrived to the full new architecture for us. But I want to take a minute and tell you it like in a story. Every 1 week can create a new feature in our catalog. The catalog notifies if something changes in the catalog. There's a new feature or update one. And send notification. The Flink controller gets this notification and deploy is our deployer. Deploy a Flink pipeline. It's called statement. Flink consume all our topics, filter the data by our SQL logic, and produce the data into the filter topic that event transformer is consumed and do some transformation. I will show you it later. And put the result to our database, real-time Aerospike. We also support backfill to process and calculate the historical data. After we show all the architecture, I want to dive a little bit to each of our microservices. First, the catalog. This is how the catalog UI looks like. Very friendly UI, self-service, and no code that every engineer, product manager, and analyst can create a site and can create a new feature by his business requirements. And every feature needs to be deployed by Flink controller, our deployer. Every feature, as you understand, is a full data pipeline. And can consume many data sources, many Kafka topics. Each of these topics have a special filter and produce it to a filter topic. Every deploy needs to run smoothly. It means that we need to stop the statement for all the data sources that we consume, change the SQL, and redeploy it again from the same offset that we stopped before the change to do not lose data. But we said that we have more than 2,500 features. It's a lot of data patterns or Flink statements that we need to handle. It's really hard to do it. So another key responsibility of the catalog is to combine many features as it can to one statement by the SQL logic, and it really helps us to monitor, to maintain the system, and it helps to optimize Flink statements, Flink resources, and so much. After Flink gets a statement, filters the data, and produce the filter event to the filter topic. The event transformer consumes the filter events and also notification from the catalog and do what we called the match. Is our matcher. It means that every filter event can link to one or many features, and it's not easy to do it because every feature has a different type of aggregation, different different key to aggregate on, and different data to take from this event. And the result is one or many Aerospike commands to update our state. And all that need to be very, very quickly in high traffic. So I want to summarize the refactoring that we did. First, we replaced Apache Storm with managed solution of Confluent Flink. Flink gives us end-to-end delivery guarantee. With Flink commit and state management, we ensure that no data will be lost. Second, we get schema update. Flink gives us the ability to stop the statement, change the SQL, and rerun it again with a readable SQL. So it's really easy to maintain a readable SQL. And the second refactoring that we did is we change, in the past, we send the data over HTTP to web service. Right now, we use Kafka and Kafka client, Kafka consumer. And it gives us decoupling service. Every microservice can change the logic and upload a new version without affect any microservices that are running in production. Next one is improve reliability. Now we can consume the data, process it, and push it to our Aerospike state. And if there is something failing in this process, we can reconsume the data and reprocess it again. So again, no data will be lost. And the last one, now we can handle high throughput. If there is spike traffic, we can scale out automatically, add more pods. It means that we add more Kafka consumer to the group and process in parallel more data. To sum up, we show you the challenges that we faced and the need to redesign our real-time feature store in weak scale. And by choosing right architecture and adapting a modern technology like Flink and Kafka, we success to reliable, scalable, and more accurate feature store. And the impact was great on Wix. It was great for the Wix service, and it's really, really improved Wix user experience to our customers. And now, we talked a lot about us. Now, we love to answer if you have some question, and we may answer to you.
Any questions? Feel free. Go ahead.
Please, some question.
Hi there. Great talk. You talked about some of the challenges with data loss, particularly when having to roll out new features, etc. Where you're using Flink SQL and obviously where schemas update, etc. How are you handling the change in redeploying? Because if you've got state built up and you've changed your schema, Flink SQL doesn't tend to offer the ability to do that state migration that you would have got at a lower level API. So how do you handle the ability to redeploy and resume from where you were, where you've got built up state?
Yeah, sure. It's using a plain Kafka consumer, and it's managed. The committing of the offset is managed by Confluent. So whenever we need to update a query, so like every streaming engine, we need to restart the job itself. If we're using a lower level API, if we're using SQL, then we still need to restart the query, right? So in this case, we're restarting the query using the API of Confluent eventually. So we just stop the query and start it again with the updated query using the latest committed offsets.
So have you been taking advantage of checkpoints and save points within Flink to allow that kind of state resuming as well?
Yeah, well, the thing is that our queries are stateless, so no worries about that really, but still it is managed by a Confluent.
Wonderful, thank you.
Hi, that was a great talk, thank you. Quick question about the cost, the operational cost of things. When you deployed from the previous legacy system to the Apache Flink-based solutions, what were your observations about the operational running cost? Was it cheaper? How was that?
I think Wix is a big company, and we have a lot of working with Confluent, so the prices was much fun.
Eventually, like the cost of maintaining our own infrastructure, we wanted to add auto-scaling and easier integration. And so the cost eventually of using the Confluent platform gave us the opportunity to be a lot more flexible and time to market much faster. So eventually, I think that the cost pretty much I don't know. It's like eventually it boils up into being pretty even better in terms of infrastructure, because in terms of integration, security, auto-scaling, these are all massive amounts of work in our infrastructure. So eventually, at least at the moment, we're glad in terms of cost at the moment.
Hello, that was a great talk. I like working with Flink, and I used to work with Flink a lot, and I know one of the challenges that very often happen is data skew, and I'm curious if you have any interesting call-outs, whether you face the problem of uneven distribution of the data across different task managers like slots, and what the performance implication that can bring. How do you tackle that?
Personally, our team is not responsible for managing the source of the data source. We're not the ones to manage the source data, so we can't really talk much about it eventually. So we're not the ones responsible really for handling this kind of stuff, because we're pretty much the consumers of the data. We're not the producers of the data.
Okay, I think it's...
Feel free to ask really any question you want.
Hi, thanks for the talk. You did mention that you are using the aggregator for the SQL, that most of the features should come into one SQL. So what if not all the features comes into one SQL? Are you executing another Flink job, or?
Yeah. Right now, we have less than 100 statements that are running. So we can combine it together, but if by the SQL logic and the data source and all that, if there is a new feature based on new data source, we need to create a new Flink statement only for this feature. We have some, but mostly we can combine from 2,500 statement, we combine to less than 100. So if there is one, it's one for each feature, it's okay.
I think you were talking about the aggregation itself, or about
The Flink. Yeah.
So I'll talk loud. So when you're creating the aggregation, like okay, let's say 10 features comes into one SQL. So you're running a one Flink job, right? So
Yeah.
what about the other features which is come into another SQL? So you're gonna trigger another Flink job.
The aggregation itself, at the moment, we're using plain Java in the transformation phase. We are planning to migrate into Flink eventually. This was all part of pretty much a migration plan, because at first we're using a very legacy tech and legacy everything. So we needed to make things a lot more prepared for our next phase, because eventually we're consuming from a Kafka topic, producing to a Kafka topic. Eventually, if you will want to replace the transformer, it would be now a lot more, would make a lot more sense to do it now. But at the moment, it works pretty good, actually. We're having like 3,000 features, and they're all being aggregated in a pretty efficient way. In the future, when we will add a lot more sophisticated aggregations, we will use Flink jobs for aggregation. But yeah, at the moment, I totally agree with you. This is probably the most prevalent question, why you're not doing the aggregations with Flink itself, which makes a lot of sense.
Okay, so if there's no other questions.
So